Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
We have been going through a course of lectures intended for the paper on physics of materials, and especially we are going through at present the chapter on crystal structures and properties of materials. In this lecture 12, the contents will be Miller planes for cubic systems, problems, Wigner size cell, reciprocal space, Brillouin zones and their importance. I have been telling you for quite some time the importance of the planes in crystals. I told you in the previous lectures, if you take a piezoelectric material wherein you convert mechanical energy into electrical energy, or the inverse piezoelectric effect wherein you apply a alternating potential and make the crystal to vibrate. Why do you make the crystal to vibrate, and what exactly you are getting from that? By making the crystal to vibrate, you develop what are called thickness vibrations, or you produce ultrasonic waves. And all of you know the profound applications of ultrasonic waves. The ultrasonic waves can be used to check the icebergs. You know, the Titanic ship sank because of iceberg which was present in the sea, and so the mishap which occurred for Titanic could have been saved if people would have taken enough care using a sonar, the sound navigation and propagation. In a sonar, the presence of iceberg. Not only that, there are more serious things like enemy submarines. These things can be detected, and I told you about biological applications like the presence of gallbladder stones in the human system, or even the sex of the baby can be determined using ultrasonic waves. Now, when you think of ultrasonic waves where you convert electrical voltage into mechanical vibrations, or you talk of electromechanical coupling coefficient. This electromechanical coupling coefficient, that is the efficiency of electric energy being converted into mechanical energy or development of intense ultrasonic waves, it varies from plane to plane. The plane across which the voltage is applied, an alternating voltage may be applied. This may be your piezoelectric crystal. You are applying an alternating potential between the two phases, and the crystal will begin to vibrate. It sends the ultrasonic waves. Okay. So, which phase you have to choose, whether you have to apply the voltage across these two phases or between these two phases, and the electromechanical coupling coefficient depends upon the crystalline plane. Which plane you choose, depending upon the plane, the electromechanical coupling coefficient will vary. Now, with keeping this in mind, you should know how to designate a plane, how to designate a crystalline plane. That is what we are trying to do. Miller gave what are named after him, the so called Miller indices. The Miller indices refers to a crystalline plane. How will you designate a crystalline plane or differentiate one plane from the other plane? Now, for instance, you take this plane shown by colored face, you got a plane like this which cuts at unit length at along the x direction, the vector A at 1 times A in the x direction, the first plane terminates at point 1A, right, cross here at 1 times A, it continues indefinitely in the y and z directions. Now, you know it cuts only along the x direction, it does not cut along the y and z direction. Okay. This is a plane that I am talking about, it cuts at 1 times A, it does not make any intersection along the y and z direction. If that were the case, the numbers which are to be taken into account are 1, infinity and infinity, and then you have to take the reciprocal, right. What will be the Miller indices? In this case the Miller indices will be 1 0 0, because you take 1 by infinity, that will be 0, 1 by infinity, that will be 0. The Miller indices are written within this kind of brackets without any comma, right. The HKL, right, you write the 3 numbers HKL, they refer to the so called Miller indices. Now, let us look at cubic faces. This cuts at 1 times A, and whereas this yellow colored face, it does not cut at along the x direction, but it cuts along the y direction. Okay. It does not have an intersection along the x and z directions. Therefore, I will have infinity 1 and infinity, right, is that right. The plane you have got the green plane that has got the infinity 1, because it cuts the z direction at 1 times A, but it does not cut the x and y directions. So, it is infinity 1. Now, let me ask you, what are the Miller indices of the 3 planes? The Miller indices for this plane is 1 0 0, for this plane it will be 0 1 0, for this plane it will be 0 0 1, right. The Miller indices, how they are obtained should be known. So, by convention Miller indices are reciprocals of the parameters of each crystal phase. The pink phase which I showed you earlier, pink phase 1 infinity infinity. Now, take the reciprocals 1 by 1, 1 by infinity, 1 by infinity, as I told you earlier 1 0 0. So, you write HKL, now they are called the Miller indices. So, 1 0 0, it is the Miller indices for the pink phase. For the yellow phase it will be, you take the reciprocals 1 by infinity, 1 by 1, 1 by infinity. So, 0 1 0. The green phase similarly 1 by infinity, the reciprocal of this 1 by infinity, 1 by infinity, and 1 by 1 is 1. So, it is 0 0 1. Now, therefore, for the pink phase it will be 1 0 0, yellow phase it will be 0 1 0, green phase it will be 0 0 1. So, there are the Miller indices that are given again here, you do not put any comma, right. Miller indices are placed in parentheses, in brackets with no commas and no fraction, they are the integers, right, Miller indices. Pink phase, as I told you, you have 1 0 0, yellow phase 0 1 0, green phase 0 0 1. Supposing you have a fraction is the intersection made by a plane along the y direction, then 1 by 2 half the intersection made by another plane along the z direction. If that were the case, then you have to convert this, it will become 4 3 2. You take the inverse of them, and then as I told you in last lecture, you have to take the LCM, least common multiple, and that will take you to 4 3 2. This will be your Miller indices for a plane like this which cuts at 3 by 4 and 1 by 2 along the y and z directions. The opposite sides of each phase are designated with negative signs. If these phases cut along the negative intercept, then you will be having minus sign, and I will come to that point a little later. This plane cuts all the three crystallographic axes. You have a plane here, that plane cuts at along the x direction at 1 times a, cuts along the y direction at 1 times a, along the z direction again 1 times a, right. It is a cube, so 1 times a, 1 times b, 1 times c, that is along the y and z directions. Because it is a cube, you have got a here, a here, a here, because at 1 times, that means your this plane will be a 1 1 1 plane, right. The number of atoms which will be carried by a plane like 1 1 1 will be different from the 1 0 0 or 0 1 0 planes, right. You take a body centered cubic structure, then a plane you can have which cuts the atom or which carries the atom at the body center, that will be different from the plane that you talk along the face diagonal, along one of the faces, right. Planes will be different, depending upon the planes the properties will be different. This again is another example. This time the plane of intersection, it cuts two of the axes, not all the three. It is cutting along the x direction 1 times a, then y direction 1 times a, but it does not cut the z direction. So, you have got a plane like this, right, a plane cutting along x and y, and but not this is a plane, right, this is a plane that goes like this. I am talking about a plane here, right, it goes like this, and then it cuts at the x direction, y direction, but not the z direction. Then that will be the Miller index for this plane will be 1 1 0, okay, 1 1 0, because it will be have infinity, 1 by infinity will become 0, okay. Then you have a plane somewhat tricky. This plane cuts two of the crystallographic axes, but not equidimensionally. The coordinates are for this plane half times a, right, is half times a, along the y direction 1 times a, and so half a and 0 a here, right. So, the values will be 1 by 2 1 0, but you have to take the reciprocal, right. So, if you take the reciprocal multiply by 2, it will be 1 2 0. So, this plane which makes an intersection half times along the a along the x direction will be referred to as a 1 2 0 plane, okay. I think by now should have a clear idea about the Miller indices, but anyway, for the sake of clarity I will again go through some of the methodology adopted is well known to you by now. Let us look at again the cubic system, try to recall how we designate the different planes. Now, a plane like this, right, what about this plane? It I am referring to a plane which has made an intersection at 1 times a, that is 1 0 0, okay. Then you have got a plane here along the z direction, it is 0 0 1, along the then a plane like this it will be 0 1 0, which makes an intersection along the y direction. Now, this is a plane about which I was talking, it does not make an intersection along the z direction. This is a plane I was mentioning now, a plane that cuts 1 times a along the x direction, 1 times a along the y direction, you see, but it does not intersect the z direction. It does not intersect means what? The numbers will be 1 1 infinity, okay, but the reciprocals will be 1 1 0, okay. The 1 1 0 will be this plane will be referred to as a 1 1 0 plane. This is the plane I was talking to you once again. It makes an intersection at 1 times a. We have been talking about the lattice planes of a cubic system, the various planes you have got here, and let us now talk about a plane like this which cuts at 1 times a, 1 times b and 1 times c. So, the intersections will be 1 a again 1 a again 1 a, right. in a cubic structure. So, the things will be 1 1 1, obviously the reciprocal also will be 1 1 1. So, such a plane will be called a 1 1 1 plane. Now, let us now pass on to a family of planes, right, it is very important. You have a plane like this which makes the origin is here. Let us focus our attention along the x axis, right, this is x axis. Now, you have a plane which makes an intersection at 1 times C, then you got another plane you got here which makes an intersection at 2 times C along the again the x axis, then there is another plane which makes an intersection along the x axis at 3 times C. So, you got 1 E, you got a plane which makes an intersection. There are 3 planes, each plane obviously should be parallel, move from the origin 1 times C, the another plane 2 times C, the third plane 3 times C. Okay. Consider the plane in the pink, right. It is actually one of an infinite number of parallel planes, each consistent distance from the origin. That is, the intersection which is made by the first plane is 1A, the second and third planes are 2A and 3A, right. Now, the family of planes that you have got here, a parallel plane which is at a different distance from the origin of the particular unit cell being considered, right. Now, this plane will be making 2 times C will be 2 infinity infinity, infinity will be 0, 2 0 0 thing that will be having here. Now, 2 0 0, 3 0 0 all will be parallel to 1 0 0 plane, and so this 1 0 0 plane refers to not only a plane that cuts at 1 times C, it is also a plane that cuts 2 times C, 3 times C, because it is a family of planes. So, there will be only 1 0 0 refers to not to a single plane, but a family of planes. Now, this plane and this plane, all the planes which are parallel to each other will be referred to as a 1 0 0 plane, right, a family of planes, right, because they are parallel. Now, so far we have been talking about planes intersecting along at the positive direction, right, from the origin 1 times C or 2 times C or 3 times C and so on. Supposing it makes an intersection along the negative x axis or negative y or negative z, in such a case what should be done is, if any of the intercepts are at negative values on the axis, then the negative sign will be carried through into the Miller indices. In such cases, the negative sign is actually denoted by overstriking the relevant number. Supposing I have a plane which cuts along the z direction, right, and the negative side of the z direction, and at 1 times A in a cubic case, then you will have 0 0 minus 1 for that plane. That will be the intersection is made along the negative z direction. That is the reason I put minus 1, but when you write the Miller indices, this minus will be referred to as 1 bar. You see, you put a bar over the number, the bar refers to the negative intersection. Whenever you got 0 0 1 bar or 0 2 bar 0. Now, whenever you got a bar, that means the intersection that a plane has made is along the negative of the particular axis. It may be the cutting may be along the x or on the y or along the z, or all of them also can be negative. If all of them could have been negative, maybe 2 bar 1 bar 1 bar. So, a bar refers to the fact that the plane which I am talking about has made intersection along the negative of the axis of a particular axis or the 2 or 3 axis. That should be remembered, right. This is a very important thing. So, what I am trying to tell is, a family of planes which are parallel to each other will be referred to by only one a set of integers in the HKL. HKL refers to, suppose I put 1 1 1, that means 2 2 2, 3 3 3, all the planes which are parallel will be referred to as only 111. Okay. 111 refers to not only single plane, but a family of planes which are parallel to each other. That is one point. The second important point is, if a plane makes a intersection along the negative of x or y or z depending upon the direction of the axis, then you put a bar over that. The bar indicates the intersection has taken along the a particular axis. Okay. Let us now look at some of the problems. Now deduce the Miller indices of planes whose intercepts are 0.4242 and 0.183. The intersection, you should remember, are not integers, right. Axial units are ABC 4242 0.367. The intercept made along the x axis is this much. Now let us write, as I told you earlier, PA is to QB is to RC. ABC are the vectors along the three directions. Now the same numbers P, Q, R are given like this along the A and B and C directions. So that is PA is equal to 424. So P into A will be 424, P into 424 is equal to 0.424. So P will be equal to 1. Similarly QB will be 2, Q will be equal to 1, and R will be equal to half, right. This is the value that you are having here. So R will be equal to 1 by half, H will be 1 by P, K will be 1 by Q, and L will be 1 by C. H, K, L are the Miller indices. So the Miller indices of this plane is given by 1, 1, 2. You can calculate the interplanar separation, the distance separating the two planes. You got a plane here, the distance separating the two planes. For a cubic system, it will be D will be equal to A by square root of H square plus K square plus L square, where you know H, K, L are the Miller indices. Let us determine the spacing between 1, 0, 0 planes, right, 1, 0 planes. Other things I am leaving it to you, that is 1, 1, 0 and 1, 1, 1 planes, you can do it leisurely. Now the atomic radius of lead atom is given as 1.746, which has got a FCC structure, and you are asked to determine the spacing between 1, 0, 0 planes. Now 1, 0, 0 means H, K, L or 1, H is 1, K is 0 and L is 0. Now the lattice constant A for FCC structure is 4r by 2 to the power of half. So therefore you will have your lattice constant R is known 1.746. Substitute the value of R here, calculate A turns out to be 4.93 angstroms, that is the cube length for the FCC unit cell. Now for 1, 0, 0 plane, that means 1 will be here, 0 here, 0 here. So 4.93 comes here, then the other things are 1 square plus 0 to the power of. The interplanar separation along the 1, 0, 0 planes will be 4.93 angstrom units, right. Now let us talk about a very important thing given by Wigner and Seitz. We have spoken about lattices in the first or second lectures. You talk of infinite network of points, ordered arrangement of points in space. Now you may have a point here, you should have a point here and point here. At the end of the blue lines, imagine that you have got lattice point, right, and take the perpendicular bisector, right, take the perpendicular for this plane, for this line, this is the midpoint, take the perpendicular bisector, right, you are bisecting the thing, right. So and this is the midpoint, then this is the midpoint, this is the midpoint, and take them, draw the perpendiculars. The area enclosed by this region is known as the Wigner-Seitz cell. The very famous people, Wigner-Seitz, they constructed what is called a Wigner-Seitz cell, that is very important. Let us now pass on to what is called the reciprocal lattice. This is the direct lattice. So far been talking about crystalline planes directions and so many other things in direct lattice. We now pass on to what is called a reciprocal space. Now, in the earlier lectures I have told you about the primitive translation vectors. How do you generate a lattice? Using the vectors A, B, C, you generate the lattice. Now, using those vectors, now I am going to find the primitive translation vectors in the reciprocal space. The reciprocal lattice vectors A, B, C are the unit vectors in the direct lattice. Therefore, let me repeat, if A, B, C are the primitive translation vectors in direct lattice, then you can define the primitive translation vectors in the reciprocal lattice, capital A, capital B, capital C. You have got a cyclic relation A is equal to 2 pi times B cross C, B will be 2 pi times C cross A, C will be 2 pi times A cross B, right. Now, the volume cell A dot B cross C will come in the denominator, the volume cell. Okay. The unit cells and primitive cells can also be defined in this lattice. As every lattice is characterized by 3 lattice vectors A, B, C, we can form a corresponding reciprocal lattice with lattice vectors A, B, C defined by the following relations. When you know the direct lattice vectors A, B, C, which are the small letters, then you can define the translation vectors in reciprocal space capital A, capital B, capital C. Now, what about the direction of A? The direction of A will be along B cross C, that means perpendicular to the plane B and C, right, or capital A will be in the same direction as that of the small a, right. If it is a cubic lattice, then A, B, C all of them will be equal. So, B C by A, B, C, that will be 2 pi by A, right. It is called a reciprocal space because A will be 2 pi by A. So, A comes in the denominator. So, what is the dimension of A? A will be, if small a is centimeter or angstrom, capital A will be angstrom inverse. Let me repeat it again. For a cubic lattice, we will have A, B, C will be equal. So, you will have A square here and A cube here in the denominator. So, it will be 2 pi by A, right. A square by A cube will be 2 pi by A here. So, A is in angstroms, capital A will be angstrom inverse. That is the reason why it is called inverse space or reciprocal space. We talk of a reciprocal lattice or a Fourier space associated with the crystal. Now, what is the importance of the reciprocal lattice vectors? This is again the beginner size cell in reciprocal space. Now, earlier I was talking about a direct lattice. Now, I have generate with the lattice vectors A, B, C, I can generate a reciprocal lattice, right. From here you have A and B and okay, you generate a reciprocal lattice, and the importance of reciprocal lattice will be known using what are called Brillouin zones. Let me now pass on to the summary of the talk. Miller indices of all planes which are parallel to each other are denoted by the same smallest set of integers. A plane which has a negative intercept on any axis will be represented by a number with a bar. Bigger size cell is obtained by connecting the perpendicular bisectors obtained by the direct lattice. We will pass on to the question session. The first question: how do you represent a plane which has got a negative intercept along a particular axis? The second question is whether planes parallel to each other are represented by different sets of Miller indices. Okay. What is bigger size cell? What are reciprocal lattice vectors? With this we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.